Hi, today we're going to talk about applications of exponential functions for exponential growth and decay. So this is a formula that should be familiar. A equals p times e to the power rt. P in this case is going to represent the initial amount of something that we're working with. R is the rate of growth and t is the time. One thing to keep in mind that the rate may not be per year and the time may not be in years. It depends on the problem. The growth problems, that's when quantities increase, the value of r is going to be positive. And decay problems, that's one thing you have to keep in mind, is the rate will be negative. So when the percentage is given to you, you got to make sure if it's a decay problem, you are going to make sure that when you put it in, it's going to be a negative number. You do need to get your calculators ready here because we're going to need to use it. Here's the first problem. The population of Newville was 20,400 people in 2015 and it increases 15% each year. So the first thing we need to do is write an exponential model for the population in terms of t. T is the number of years after 2015. So this is the initial amount. This is the rate, which is going to be 0.15. Okay, so then it's going to be A equals 20,400 e to the power 0.15 t. My apologies about that. Okay, that's all you need to do here. You just need to write an exponential model. The next questions will ask you to do something with it. So using the model from part A, find the population in 2024. So let me rewrite this model again. I also wanted to point out that we have a growth situation, the population increases, so the value of R is positive. 2024, that's 9 years later, so T is going to be 9. You are going to write it like that. And then use your calculator, any calculator that can do all this work. So it's going to be 20,400 times e to the power of 0.15 times 9. And we're going to get 78,691. We're really not going to worry about these decimals here because we're dealing with population, people. So it has to be a whole number, 78,691. Now the third question is, when is the population going to reach 100,000? So we know 9 years later it's going to reach that number, but what about 100,000? So the first thing we're going to do here, this is the value of A that's given to us, and we're trying to find T. So we are going to set up the following equation. 100,000 equals 20,400 e to the power of 0.15 t. T is what we're looking for. This is a pretty typical form of these exponential equations, and they're all going to be done the same way. The first thing you're going to do is divide both sides by 20,400. So it's going to be 100,000 over 20,400 equals e to the power of 0.15 t. This is an exponent. Now you could divide this, but it's going to give you decimal, and I always recommend waiting on that until you get to the very end of the problem, and then you can just put the whole thing in the calculator. So this is a number, equals e to the power. You rewrite this in the logarithmic form. So it's base e, so natural log of 100,000 divided by 20,400 equals 0.15 t. And to get t, you're going to take this natural log of that whole thing and you're going to divide it by 0.15. That's precisely what we are going to do. So ln 100,000 divided by 20,400 and divided by 0.15, and that's going to happen in, I'm just going to say 11 years. 10.59 during year 10, it's not going to be quite there yet, so 11 years. So in 11 years. So in our case, since we started in 2015, it's going to happen in the year 2026. Okay. Next problem. A brand new car was purchased in 2018 for 16,000. The value decreases by 22% each year. So this is A. The value of R is going to be entered as a negative number. Okay. So for the exponential model, you're going to write A equals 16,000 e to the negative 0.22 t. Here's what's going to happen if you don't put it as a negative number. You're going to end up getting a larger number here when you should have a lesser number. So this is how you would know, but there is no, when you are going to do these problems, it is never going to tell you that R is going to be positive or negative. It is up to you to determine that. So 5 years later, how old is the car? 16,000 e to the power negative 0.22 times 5. Get our calculator. And it's going to be valued at about $5,326. We're not going to worry about the cents. When we buy a car, we don't really worry about pennies. And the question is, how old will the car be when its value is going to hit $3,000? So this is the value of A, and we're looking for T, right? So we're going to set up the same exact equation we did in the previous problem. So A equals 16,000 e to the negative 0.22 t. This is going to be replaced with 3,000. We're going to divide both sides by 16,000, so it's going to be 3,000 divided by 16,000, which I'll simplify by canceling out the zeros. I'm still not going to divide it, but I'm going to continue here. So we're getting 3 over 16 equals ln, oh, I'm sorry, it's still E. Let me fix this. 3 over 16 equals e to the negative 0.22 t. ln of 3 over 16 equals negative 0.22 t. So here we're going to have that t is going to be ln 3 over 16 divided by negative 0.22. Plug it in the calculator. Let me do it here so you can see it. So we do ln of 3 divided by 16 divided by negative 0.22, and our car is going to be about 8 years old. 7.6 years. Now, depending on what the problem is asking you, how the problem is going to ask you to round the answer, that's what it's going to be. Right. Next problem. Population of certain bacteria grows at the rate of 35% per hour. 300 bacteria. So our expression is going to be grows. It's going to be 300 e to the power of 0.35 t. 6 hours. It's going to be 300 e to the power of 0.35 times 6. Calculator time. We're gonna have about 450 bacteria. We're dealing with bacteria, so we can't really allow decimals. In how many hours will there be 4,000 bacteria? So we're going to set it up as 4,000 equals 300 e to the 0.35 t. Divide both sides by 300. I can cross out 2 zeros here to make things a little bit easier. So we're going to have 40 over 3 equals e to the 0.35 t. ln 40 over 3 equals 0.35 t. So t is going to equal ln 40 over 3 divided by 0.35. Plug it in the calculator. So ln 40 divided by 3 divided by 0.35, we get about 7.4 hours. So one thing that I wanted to point out here is, since we had hours for the rate, then t is hours and everything is going to be consistent. This is what I meant when I said in the beginning that it may not be years and does not have to be, and it could be any time unit. Okay. And our final problem here, we're dealing with some radioactive isotope whose amount decreases by 16% per century, and at one point we have 20%. And so to write the model in the number of centuries, A equals 20, E decreases negative 0.16 t. 3 centuries later, 20 e to the power of negative 0.16 times 3. So in 3 centuries we're going to have about 12.4 grams. And then in how many years will there be half of the original amount? So half of the original amount is 10, right? So it's not always going to tell you the exact number. Sometimes it's going to tell you things like double, half, or anything like that. So you should be able to do that. So we're looking for half. So that's 10 equals 20 e to the negative 0.16 t. Divide both sides by 20. And what's going to happen here, you're going to get a half, right? Which is going to be consistent. We want half left, right? So it's going to be representing half. Then ln 1/2 is going to equal to negative 0.16 t. And t will be ln of 1/2. We're going to divide this by negative 0.16. We'll plug it in the calculator. And we're going to get t equals, so there's going to be 4.332, etc. But one thing that I want to show you here, in how many years, because remember, t represents centuries. So if we want to get that in years, we're going to take this number and multiply this by 100, and that's going to happen in about 433.2 years. Okay. So 433.2 years, and that's how these problems are done. I hope this helps.